are solids. There may be a few exceptions, but for the vast majority of them, they're going to be solids. And we know that there are three primary states of matter: solid, liquid, and gas. There are some other kind of fringe solids out there that are a little bit more theoretical, but we're going to focus on solids. And you may already know that there are two primary types of solids. There are crystalline solids, and then there are amorphic solids. We can break those down a little bit more, and so we have polymorphic solids. A polymorphic solid is a crystalline solid that is capable of existing in multiple crystal structures. And so remember, when a compound or a molecule goes from the liquid state to the solid state, in a crystalline solid state, the molecules or the atoms are going to form a very unique structured form. However, that form can be in different shapes. And so on our slide here, we see polymorph A and polymorph B. We can see that the molecules that make up that crystal are chemically identical to each other. However, in polymorph A, the molecules kind of face the same direction as each other, where in polymorph B, they face opposite of each other and they can pack a little bit closer together. Depending on how the molecules pack, we get different crystal structures, and different crystal structures can have very, very different properties. It may melt at a different temperature. It may dissolve better or worse. It may be more or less stable. Something else that we have to be concerned with is pseudo-polymorphism. In some situations, it may look like two samples of the same compound in the solid form have different crystal structures, and we think that they are polymorphic. When in reality, what we're looking at is pseudo-polymorphism, where trapped in the crystal structure are solvent molecules. Almost always, when we make a compound using organic chemistry, it's going to be made in the liquid phase. We're going to be dealing with solutions, and then we need to, number one, recrystallize that compound in order to purify it, but then we also need to get rid of all of the excess solvent. And getting rid of all of the solvent is very, very difficult, particularly if there's some sort of affinity between the drug and the solvent. And so we may end up with what we call a solvate, where we have the molecules of our drug, and trapped in there are solvent molecules. So on the right here, this is some sort of organic solvent. On the left, it is water. Now we have water all around, right? And you've probably heard the term or hygroscopic compounds, right? When you dealt with organic chemistry, if you took organic chemistry, you probably had to worry about leaving containers open because they might absorb some of the water out of the air. And so this is not necessarily a matter of getting rid of water, but it's a matter of preventing the water from getting in there. In either case, if we have solvent trapped in our crystals, it's very much going to change the property of those crystals. Then we have the amorphic solids. Amorphic solids do not have a defined crystal structure. The molecules are just randomly thrown about. Amorphic solids can be thought of as liquids that have a very, very, very high viscosity. Probably the best example of an amorphic solid that you're familiar with is glass. Something you may or may not have heard before is that glass, over decades, will get brittle at the top, because over time, the molecules and the atoms slowly fall down. It is acting like a liquid. It is fluid. It is changing shape over time. If you put glass in a container, it will eventually take the form of its container, but it's going to take maybe hundreds, if not thousands, of years. So in reality, in practical terms, an amorphic solid is a solid. However, theoretically, it can be thought of as a liquid. Depending on which state we are in, whether we're in polymorph A, polymorph B, solvate A, solvate B, or whether we are amorphic, we're going to have very, very different properties. And not only are we going to have different properties, but they're going to behave differently when we subject those solids to heat. And so depending on how they behave, we can gain some information about which form we are in. So let's talk a little bit more about polymorphisms. So I said polymorphisms are crystal structures made of the same molecules that form different structures, right? There are two primary ways that we get different polymorphisms. Number one is how quickly we formed those crystals. Normally, we recrystallize things. We dissolve them at a high temperature so that they dissolve better, and then we just lower the temperature so that the solubility decreases and we form crystals. But how quickly we cool that solution down will determine how quickly the crystals form. And the slower they form, the more time the molecules have to get to the ideal arrangement. If we have impurities, we can also get different polymorphisms. Think of this kind of like a solvate, but these may be molecules that are very similar to our drug molecule and actually form an integral part of that crystal structure. So on the right, we have a picture containing 4 different polymorphisms of a drug. And so if you look up this paper, you'll find a story about how they identified this drug and they had polymorphism A. And then eventually they found that in actuality, they had 2 polymorphisms. They had form A and form B. And then in the process of studying form B, they no longer could actually produce form B, even if they tried. At that point, they had form A and form C. And then as they continued to study the drug, they eventually then found form D. And so these are scientific researchers who know what they're doing and struggle with getting a consistent polymorphism. But this is very, very important because these polymorphisms are going to have very different properties. One may be more stable than the other. How long is the shelf life of these drugs? One may dissolve better than the other. If I take a pill and that drug does not dissolve in the aqueous environment in my body, it's not going to do me any good. Not only is it going to dissolve differently, it may be absorbed differently. It may distribute differently. It may get metabolized differently. It may get excreted differently. All of these properties that we worry about with drugs are dependent on that crystal structure. And if we have different polymorphisms, those properties are going to be different. So like I've been alluding to, one way that we can analyze this is through thermal analysis. There are a lot of different techniques that use thermal analysis. All this refers to is using heat to analyze something, right? But the most common method that we use, and the one we're going to spend the most time on, is called differential scanning calorimetry, or DSC. This is a quite common technique of analyzing things. Number one, because it's very cheap. We're going to see there's no expensive solvents or reagents or anything. We just put a sample in there, we heat it up, and we see what happens. Taking DSC and breaking it down into its simplest form, what we're going to be doing is we're going to be measuring the absorption and or the release of heat from our sample. And if we look at the name differential scanning calorimetry, it tells us exactly what we're dealing with. So differential, when we look at DSC, we're going to be comparing two samples. We're always going to have a reference and then the sample that we are actually measuring. So we're comparing the differential between the two. The scanning comes from the fact that we start at a low temperature and then we slowly heat the sample up, or we start at a high temperature and slowly cool the sample down. So we're going to scan a range of temperatures. And then the word calorimetry just means that we are measuring heat. We can get a lot of information from differential scanning calorimetry, some of which is qualitative, some of which is quantitative. So remember, a qualitative property is more of a yes or no thing. Is it this? Is it that? There's no numbers involved. For example, when we heat a sample up and a process occurs, is that process exothermic or endothermic? There's no numbers involved there. It's just kind of a, is it this or is it that question. But we can also get quantitative data using DSC. Quantitative data involves numbers. We are measuring something, such as what is the heat of fusion of this compound. Now, I'm not going to ask you what the heat of fusion is, but if you don't remember from physics or chemistry, the heat of fusion is the amount of heat that is released when a compound goes from the liquid state to the solid state. Now, this is very important. We use the term differential scanning calorimetry, or DSC, kind of globally. But in reality, there are two very distinct types of DSC. Luckily, they give us the same information, and they give us a output, sort of a graph that we're going to see coming up that is basically the same regardless of which type of DSC we're using. But it's very important to realize that we have two types because they work differently. We have power compensation DSC and we have heat flux DSC. Now I'm going to start with power compensation DSC because in my mind it's a little bit easier to wrap your head around, even though it is the less common form of DSC. So in power compensation DSC, we have two little areas of our instrument, okay? We are going to call each one a furnace, okay? Think of it like an oven. It is a thermally isolated, insulated area, okay? And then we're going to put something in there, and we have the ability to control the temperature inside of that oven. So in power compensation DSC, we have two separate ovens. In one oven, we have our control or our reference, and the other one we have our sample. Now, we're dealing with solids. Think of a powder. We need to put them on something. And so that's this pan. We have a reference pan and a sample pan. Think of it like it's usually a little aluminum foil pan, like a pie dish, okay? But it's about that big around, and it just sits in there, and you put your sample on top of it. So now we have two ovens, each with a pan in it. One of those pans has a sample on it. One of them is just an empty pan. Our goal is to heat both ovens up at the same rate. Now, it's not difficult to visualize that the oven that contains the sample is going to heat up slower than the oven that doesn't, okay? Imagine you have two ovens in your home, side by side, and you put a turkey into one, and you leave the other one empty, and you try to heat them up at the same temperature. Heat them up at the same rate. In order to get the oven with the turkey to heat up at the same rate, you're going to have to pump more heat into it, because that turkey is going to be absorbing a whole lot of heat. And so in our DSC instrument, we're going to have to put more heat into the oven or the furnace that contains the sample than the reference pan. And so what we do is we compare how much more heat are we putting into the sample pan versus the reference pan. And the amount of the differential between them is going to give us some information. And so in this case, we are going to adjust the amount of energy or the heat that we are putting into the two furnaces so that we obtain the same temperature or maintain the same temperature between the ovens. The more energy that we have to put into our sample oven, that means that our sample is absorbing more energy. The heat flux DSC instrument is, in my mind, I don't know. I'm not going to say it's easier. Maybe for you it'll be harder. Maybe for you it'll be easier. But imagine the situation where we have one oven, and in that oven we put a turkey and a chicken, and then we turn up the heat in that oven. There's no way that we can control the temperature on one side of the oven versus the other. So in that situation, the small chicken is going to cook faster than the large turkey, right? The larger turkey is going to have to absorb more energy in order to increase its temperature. So in heat flux DSC, we have one furnace. We apply the same amount of energy to the two sides, the sample side and the reference side, and then we compare the change in temperature. Sorry. That word here should be temperature. Hopefully as soon as I finish this, I'll remember to change that. We're going to look at which pan, the sample containing pan and the reference pan, is changing temperature faster. The turkey is going to change temperature slower than the chicken. So I'm going to stop here for this video and then pick up in the next one.